Hello, everyone. Welcome to Theo-MathProblemSolver. I'm excited to take you through some key concepts, even as we kind of look at how best we can relate them to real-world situations. So our objective today is to try our best possible to classify the relative extrema of a function using the second derivative test. And if time permits, we would look at how best we can graph a continuous function in a manner that shows concavity. So stay with me even as we explore them together. All right. So, so suppose that f is a function whose, you know, whose derivative, which we denoted as f prime, okay, whose derivative, which we denote as f prime, exists at every point in an open, interval, open. So so let me underline those key words. We have every point in an open interval. So in the previous episode, I elaborated on all of these. But then at this point, I also kind of gave some illustrations so that you would have a deeper knowledge or a deeper understanding of what we're talking about. Then we claim that then F is concave up on that interval if F prime is increasing over the interval. Okay. So we claim that the function f is concave up on that particular interval if f prime is, increasing on that particular interval. So let me give you some graphs so that you would understand what I'm trying to talk about. So suppose that we are in this xy plane. So let me give you a graph over here. So the first graph. So let me call this one A and this one the B part. So I'm giving a graph of the A part. So with the A part, let me draw this one. So suppose we are in this XY plane, okay? And suppose that our X is the interval, okay? Our X, we are considering the X, but then we kind of use A and B as the interval, okay? AB as the interval. Suppose that I have a graph as this that, start at this point, our graph starts at this point. It starts at this point, then it kind of decrease and then goes up to this point. So let's suppose this is how the F looks like, okay? Then over here, we see that this is how it starts. It starts at this point, then it begins to decrease, then it goes up again. Such graph, we say that is concave up. We say that such graph open up. Okay, so we say concave up within the interval AB. Okay, is that okay? Good. So that is how, so within this interval, we see that the function starts at a very high point, then it decreases, then it goes up again. In such a scenario, we say that the graph is concave up. In other words, it opens to the heaven. It opens to the heaven. Is that okay? And we also said that in such situation, we claim that its derivative is increasing within the interval AB. Okay? Its derivative, which is f prime, is increasing over the interval AB. Now let's look at the second part of this. Now the second part of this graph is that we also said that f is concave. Let me underline that. We also said that f is concave down on the interval I if f prime is decreasing over that interval. What are we saying? So suppose I give you a graph as this. Suppose I give you this graph, okay? So we are using this graph. And I suppose that on the x-axis, we have the interval is A to B, okay? Suppose the interval is A to B. Let's say that this is how high, let me use a different pencil. So we start how, let me use a different pencil so we suppose we start at this point as high as this, then this function kind of, goes up a bit, then it kind of decrease up to this point. Okay. So over here, we see that the function was started at the point A. Okay. So you see that it started at the point A, but then it increased up to a certain point, then it begins to drop, to decrease up to this point. Do you see that? So in such manner, we claim that the graph of the function is concave down over the interval AB. When that happened, then we claim that its derivative is also decreasing. Okay. The rate of change of that particular function within that interval is also changing. Am I understood? Okay. That is the basic way to kind of explain this definition. I believe that with this graph, you should be able to kind of understand. At this point, if you have not, subscribe, please do so. Put, kind of click on the notification button so that anytime I kind of upload new content, you'll be the first to have them. All right, so let's move on. So we also want to test for concavity. Now we know concave up. We said that concave up is when the graph of the functions open up to the heavens, and the concave down, the graph of the function opens downwards. Is that okay? So now, how do we test for concavity? How do we test as whether the graph of the function is concave up or concave down? So there are various, instances or scenarios that we can base on to classify such, notion or such graphs that we may encounter. Okay, so let's look at them together. Now, the first thing that I want to, sort of talk about is that if the second derivative of the function is positive or is greater than 0 or is positive on an interval, okay, so let me underline that. So if the second derivative is positive over the interval I, the interval in our case, we are using AB, okay? It's like we have point A and point B. So within this interval, A to B. So that's where we are considering that as our interval. Then the graph of F is concave up. Remember that anytime it is positive, we said it's concave up. In other words, F is increasing, or the rate of change of the function is increasing, or F is opening up on that particular interval. So we use this particular, graph to talk about, okay? So we use this particular graph to talk about it. Very good. So let's take note of that. Then we also said that if, on the contrary, if f, the second derivative of the function is less than 0 on that particular, interval AB, then we claim that the graph of the function is concave down, which literally means that our first derivative is decreasing. So it turns out that it's decreasing. So it turns out that f is turning down on that particular interval AB, okay? So a typical graph to illustrate that would be this particular one. Is that okay? Good, 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 good. So let's take note of that. Now, at this point, let's see how best we can, leverage such definitions to solve a particular some problems. But then before we kind of delve into some definitions or we delve into problems, I want us to probably maybe look at one or two things before we solve examples. So let me just give you a little bit of some stuff before we kind of look into that. Okay, so let's look at the first theorem. So the first theorem is that, let me use a different pencil. The first theorem is that suppose that f is, differentiable. Suppose that f is differentiable for every x in an open interval, okay? In an open interval, let's use, as we have been using, AB, okay? And that let's say there's a critical point. So in our previous episode, we talked about critical point or critical value, okay? And we were using for consistency, we are going to use C as our, critical value in that particular interval, okay? In our interval, which is AB. For which, remember, we said that for critical value, for us to find the critical value, the first derivative, right? We said that the first derivative evaluated as C should be 0, okay? That was what we said last in our previous episode. We said something like this, that it has to be, when we evaluate it at the critical value should be 0, or the first derivative does not exist. We also pointed out, and there are instances where that also holds. If this is the case, then we need to look at some scenarios. If this is true, then we have that. So if we have that the main function being evaluated at a critical value is a relative minimum if, so let's take note, if f prime prime, or the second derivative evaluated at the critical value, is strictly greater than 0. So let's take note, it's critical greater than 0. So which we have to take note. Conversely, if f or the function being evaluated as C is a relative maximum if our second derivative, okay, being evaluated as C is less than 0. So please, I want us to kind of take note. So I want us to please take note of that. So please take note of that. All right, so at this point, what we are going to do is to solve problems. Now we know, if you look at some few definitions and a theorem to buttress our definitions, the first two definitions we gave. Now I want us to leverage such theorem and the definition to solve problems. So let's look at it together. And that I also mentioned in our previous episode, I also mentioned that when you say extrema is a collective name for relative minimum and maximum. When I say relative extrema, I mean to say that relative minimum or relative, maximum. So please take note of that. Now let's go to our first problem. Given the function f, given the function f given by, given the function f of x as this, how do you find the, relative extrema? How do you find the relative extrema? I mentioned that extrema is a collective name for maximum and minimum. So let's take note of that. All right. So how do we solve this? How do we solve this? How do you find the relative Extrema using the second, derivative test. In our previous episode, we were using, the first derivative test to find relative extrema. But in this instance, we also want to explore the case where, the second derivative test can be used to solve problems, the same problem. Is that okay? So let's look at how best we can kind of do that. So what would be the first thing to do? So the first thing to do is to get our critical value, right? So the first thing we need to, do is to get our critical value. So what would be our critical value? So we are given the function f of x. So we are given the function, so we are given the function f of x equal to what? Equal to x to the power 3 plus 3x to the power 2 minus 9x minus 13, okay? Now, the first thing to do, for us to find the critical value, we need to, since it's just a polynomial, we just have to find the first derivative and we just set 0 to find the critical value, to find the critical values, right? So the first derivative, our first derivative would just be what? 3x squared plus what? 6x minus 9. But then we know that the derivative of a constant is 0. All right. So for critical values, so for critical values, we have f prime of x being set 0. So that's for critical values. Okay. For polynomial, we just do it like this. Then we go straight away. So on that note, we're going to have, so this implies that our 3x squared plus 6x minus 9 equal to 0, right? So one can decide to just, to simplify this, you can just, divide both sides by, divide each term by 3, and that should give us what? X squared plus what? 2x minus 3 equal to 0. Now you kind of factorize this, and by factorizing, you should get what? X minus what? Plus 3x minus 1 equal to 0. And that when you solve that, you should have what? S equal to 1 or 3. Okay, very good. So we have these values. So these values as our critical values. Okay, so our critical values are 1 and negative 3. 1 and negative 3. Very good. But at this point, we are going to use the second derivative test with negative 3 and 1. So at this point, we are using the second derivative test. So we are using let me indicate something here. So I will use different pencil. So I would say that use the second derivative test, okay? So you're going to use a second derivative test for x equal to 1 and negative 3. So please, let's take note of that. All right. So on that note, we are going to find the second derivative, okay? We're going to find the second derivative of the given function. So what would be the second derivative of this function? So by using this, we need to find the second derivative. What would be the second derivative of this function? So already we know that our first derivative was given as was when we solved our second derivative, we had 3x squared plus 6x minus 9. So it means that our second derivative of this would just be what? So we drop the power, okay? Then we decrease the power by 1. So that gives us 6x. Then the derivative of 6x gives us 6, okay? Good. Then remember that the definition we kind of gave over here is that the definition we gave over here as far as the second derivative is concerned is that, let me just go back a bit. So over here, we kind of said that we need to evaluate, remember, that for the relative minimum, or at this point, since we're using a second derivative test, what we're going to do, we're going to evaluate the second derivative at the critical point, right? That was what we said. We are going to evaluate them at the critical point. And if it's positive, then we claim that it's a relative minimum. And if it's negative, then it is a relative, maximum. So I want us to hold on to this particular theorem. All right, so we're going to use that. So what happened is that we are going to evaluate them at the critical values. So at the critical value of -3, so it means that wherever I see x in this, I just replace it by -3, and that should give us what? That should give us -12, which is less than 0. So if it is less than 0, what can we say? If it's less than 0, what can we say? It means that we have what? A relative what? We have a relative what? Maximum, okay? So we have a relative maximum at -3. And then we kind of also evaluate the second derivative at 1. It just means that wherever I see x in this, I just replace it by 1. On that note, we're going to have 6 of 1 plus 6, and that should give us what? 12, which is positive, which means that at this point, we're going to have a relative minimum. Is that okay? Good, 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 good. So if that's the case, now let's collect the points or the coordinate together. So this means that, but remember that the theorem, we have to also evaluate the main function at these critical values. Remember, we have c, f of c in both instances, okay? So f of c is a relative minimum if this holds. So what it means is we also have to evaluate the function at these critical values, okay? All right. So, but now we know that our main function was what? Our main function was giving us what? Was 3 to the x to the power 3 plus 3x squared minus 9x, right? Minus 13. Now we need to, evaluate this function at the critical values. So at -3, we should get so we need to evaluate that then, and that should give us what? That should give us 14. And then we also evaluate the same function at 1, okay? And with that, you should get that should give us what? -18, right? That's so good. All right, so now this implies that, or this means that, so at -3, its corresponding value was 14. So at -3, we have it corresponding to be 14. So -3, 14 is a what? What can we say? It's a relative what? Maximum or minimum. Remember over here, we had at -3, we had relative maximum. So we say that the point -3, 14 is a relative maximum, and the point 1, -18 is a relative minimum. So let's take note of that. This is also important. So please, let's take note of that. All right. So this is the way we kind of solve this particular problem. Now, the question is, what would be the graph of this? What would be the graph of this? What would be the graph? So looking at this point, it is easy to graph because of the coordinate we have. So if you have the coordinate, it's easy to graph it. Okay, so looking at the coordinates, so let's looking at the coordinate, it is easy to graph them. Now we have a relative maximum. We have a relative maximum at -3. Suppose this -3 is here, and then the 14 is somewhere here. Then it means that here will be our turning point. Let me just lower this a bit. So if this is our coordinate, -3, 14, and then let's try to also, plot 1 and -18. So let's assume that 1 is here, and then -18 is probably here, down here. Let's say -18 is here. That means that this is a point. This will be the turning point. So on that note, you could, remember that the function was a cubic function, right? So it just means that now our maximum point probably will start at this, will start over here. Remember, this is a relative maximum, so it attains a maximum at -314. Then it would eventually decreases. So it will decrease, then it kind of, oh no, I didn't give a good graph. So let me take my time and give a good graph. So this is how we so we have it here. Good. So our -3, okay? Our -314, it was here, which is our maximum point, which is our relative maximum point. And then one, was it one? Let me use a different pencil here, which is 1 -18 at this point. Okay, so we have two turning points. The first one is the relative maximum, and then the second one is the relative minimum. I hope at this point we are okay with it. Good. So let's look at our second example. I believe by solving more examples, we should be able to understand it better. Okay, so our second example is this. So we have this particular problem. We kind of want to solve it. How do we go that? How do you go about it? So the first thing to do is to find the critical values, right? That's the first thing we need to do, is to find the critical values. How do we find the critical value? We find the derivative of the given function. And remember, we said that the derivative of an exponential function will be what? We differentiate what? So at this point, let's distribute. So we have this to differentiate. And by distributing, we're going to have, we said that the derivative of the difference of function is the what? Is the difference of the derivative, okay? That's what we said the last time. So we have this. Now, what is the derivative of 2 to the power 2x? 2 to the power 2x. And that should give us what? That should give us 2, 8 multiplying 2 multiplying e to the power x. And then the derivative of the special exponential function is always what? Itself, okay? Good, good. That's what we said. Then afterwards to find the critical value what we do is that we set the derivative to 0, okay? So to find a critical value, we set this derivative to 0. Is that okay? So that's what we did the last time. We set this to 0. So by setting this to 0, we are going to have what? So this implies that we're going to have 2 this times that minus 2 to the e to the power x equals 0. At this point, I think the easiest way is to factor the e to the power x outside, and that would make our work too easy, right? That would make our work too easy. So let's do it that way. So what happens is we are going to pull out e to the power x outside. You're going to have 2 multiplying e to the power x minus 1 equal to 0. Now, you remember that since e to the power x can never be 0, right? E to the power x can never be 0. Okay, let me say for all x, irrespective of what x value it may take, e to the power x can never be 0. Okay, whatever value x want to assume, x can assume any value, but can never be 0. So let's take note of that. So on that note, we cannot have that. Okay, so the only thing we can rely on is 2 multiplying e to the power x minus 1 equal to 0. Okay, good. Now, when you solve this, we should have e to the power x equal to what? Half, half, right? Good. Now, how do we get x? The last time we kind of look at some of the algebra of this, and we said that the natural log and the special exponential function, they are inverse of each other, okay? So then what the easiest way to solve this is to apply that natural log on both sides, okay? So that's what we did the last time. So with this, we're going to have x equal to what? The natural log of half. So you're going to have this as a, so let me use 0.5 just to, make things as easy as possible instead of using half throughout. So let's use that. All right. So at this point, what we're going to do is to use the second derivative test, okay? So I'll say that use the second derivative test, okay? So we're going to use a second derivative test. So by using the second derivative test, I would hold with the critical value lane of 0.5, okay? So with a critical value lane of 0.5. So, but what would be the second derivative? Like, remember, so far we have not found the second derivative. We only have the first derivative. Remember, the first derivative was given as what? I think we had e, I think 2 multiplying e to the power 2x minus, I think something like that. That's what we had for the first derivative. Now, what would be the second derivative of this particular function? All right. So what would be the second derivative? So we're going to have what? 4 multiplying 2x minus this, right? Now, since already we know our critical value, so we just have to plug in and we get our value. Then at that point, we can determine what to determine the type of concavity that we can have. Okay, good. All right, so let's evaluate such function at the given value. Let's evaluate it at the lane of 0.5, and by evaluating there's 2 multiplying lane of 0.5, okay, minus. So what do we get? Now, this is easy to solve in the sense that this one you can send out to use a calculator, in the sense that this one we can still simplify it, right? So we can have, by using the laws, we can have this, okay? You see, since the exponential function and the natural log are inverses of each other, they cancel themselves, right? So we're going to have what? 4 multiplying whole 0.5 to the power that, and then you have this. Is that okay? Good. So we see that this one will give us what? Let me see. That should give us 0.5. And 0.5 is greater than 0. So if 0.5 is greater than 0, what does it mean? It implies that what? It implies that we have what? Relative what? Maximum or minimum. So we are going to have minimum. Is that okay? And the last thing we need to do is that we need to kind of, find the values of the function at the critical value. That's what we said. Per the theorem, having determined the kind of the extrema that we are able to get, then we can now have to go back to the main problem. Then we evaluate the main problem at the critical values. Is that okay? Very good. So please let's take note of that. So lastly, I would say that, so let me write this. For better understanding, let me write this one. Let me write this. So I would want to also kind of point out that these are areas that instructors usually based on to test their student be. Okay, so myself, I also like this kind of problems or this kind of areas for to test my student as well. So please, if you're looking at this, I want you to make sure that you kind of take your time to understand it, so that you can always be ahead of your colleagues in class. Okay, all right. So lastly, find the values. Let me see the values of the function at what we said that at the critical value. Okay. So on that note, we are going to have, remember, our k of x was given e to the power 2x minus e to the power x, right? So if we evaluate it, if we evaluate this at natural log of 0.5, then you're going to have what? E to the power. Let me use a different. So we're going to have, so by using the rules, they should give us what? 0.5 to the power 2, and then the what? 0.5. And that gives us what? And that should give us negative 0.25. Okay. So this implies that the point, this implies that a point lane of 0.5 and negative 0.25 is a what? It's a relative what? Minimum. So let's take note. Very, very, very important. So let me just quick recap of what we've done so far. So we're given this particular function to solve, and the first thing to do, since we're using since we want to find the relative extrema, And as I mentioned, the extrema is a collective name for maximum and minimum, okay? Good. So the first thing to do is to find the critical values. How do you find the critical values? Now, we need to find the first derivative, then we set to zeros, and the values we kind of get are what we refer to as the critical values. But then when we go here, it was kind of very funny and very tricky in the sense that e to the power x can never be zero. So on that note, we have to exempt this, okay? This particular thing, e to the power x. It was very tricky. So please, let's take note, it can never be zero, irrespective of what value x may try to assume, okay? It can never be zero. Even if x is zero, e to the power zero is always one, so it can never be zero. Is that okay? So on that note, we're going to base on this particular term, which is 2 multiplying e to the power x minus 1, okay? So it's the only thing that we're going to rely on. And when we go here, we kind of, at this point, what we did was that since we want to find x, we kind of take the natural log on both sides. The reason why we're using the natural log on both sides is because a and the natural log, they are inverse of each other. They always cancel themselves. So the most, wisest way to solve this is to apply the natural log. So, okay, so that will cancel that you only have the x, okay, on one side. Good. And then we had the natural log of 0.5. And since we are using the second derivative test, okay, we have to find the second derivative, then evaluate it at the critical value. And when we did that, we saw that the critical value ln of 0.5 was evaluated at the second derivative was positive, which indicate that we have a relative minimum, okay? At this point, we are not done, but the last thing for us to do is to find the values of the given function at that critical value. Okay, so we have to evaluate the function at that particular critical value, which is ln of 0.5. And we saw that the result was negative 0.25. So which means that at a point, or at this coordinate ln of negative 0.5 and negative 0.25 is a relative minimum. Is that okay? So this point or this coordinate is a relative minimum. So that's what we've done so far. Now, I want us to look at another interesting concept. We call that the point of inflection. We call it the point of inflection. Very, very important concept. All right, so we are looking at the point of inflection. What is an inflection point or point of inflection? What is it? So it's defined as a point on a curve in which the concavity changes. So I would at this point, let me use just a graph to illustrate what I'm trying to explain. So suppose we have a nice graph as this. Let me use this graph to explain that. So suppose that we kind of have, let me use this. So we have this. Now, at what point do we have, what point on this graph does concavity, change? We see that around this point, there's a change in concavity. Okay, there's a change in concavity from this point. So from this point up to here, we have concave what? So we have the concave up at this point. And then then from here up to here, we are going to have concave what? We're going to have concave down. So we see that around this point, there's always a switch of concavity. There's around this point, okay, around this point, there's always a switch in concavity. So we move from a concave up to a concave down. So this is what we call the point of inflection, okay? So we refer to this as the point of inflection. And what does it mean, point of inflection? We said that is the very point for which there's a switch in concavity. That is concave up, moving, we transitioning from a concave up to a concave down. Is that okay? Or vice versa? Okay, very good. So let's kind of take note. But then let's go further than, let's go a bit further than what we have just explained. Let's move forward and trying to look at from a different perspective. Okay, but the basic definition is what I just explained using the graphical method. Okay, now let's look at it from the viewpoint of the second derivative. So with the second derivative, we kind of have a way of, we can kind of look at it to solve problems. Okay, so we said that a function f has a point of inflection, then put an inflection at a point. At this point, let's say maybe x naught, then the second derivative, okay, which is very, very important. The second derivative should be zero, or the second derivative should not exist. It's very, very, very important. So I want us to please take our time to really understand this, because it's important in life. Over here in life, that's how this one is really, relatable. It's as if at some point you kind of, you are enjoying a life, and at some point you switch, then you begin to struggle and all of that. So those circumstances we can say that you are at the point of inflection. It's like somebody who is happy right now, and the next minute the person is sad. So that what has occurred from you transitioning from happy to sad, is that point is what we call the point of inflection. Okay, very, very important. It's like somebody who was once poor and now he's rich. So at a point that transition took place, what we call the point of inflection. So let's take note of that. Okay, very, very, very important. Okay, so let's get the first problem of the day. And the first problem is that we are given this nice problem to solve. How do we approach this problem? How do we approach this problem? So we want to find or determine the point of inflection for the given function. Okay, so the first thing to do is what? Is to find the first derivative. So the first derivative of this will be what? So our first derivative would just be what? Would just be 30x squared minus what? 30x, okay? But remember, per the definition, we need a second derivative per the definition. So we go further to find the second derivative. So what would be the second derivative? That would be 60x minus what? Minus what? 120x to the power 3. Is that okay? All right. So that's what we have. But the definition, remember the definition said that we should set such second derivative to 0. Is that okay? Very good. So we said, because this is just a quadratic, we are just going to set to 0. If it was a rational function or some quotient, we would just have to take into account, look at the situation where this particular, f second derivative may not exist. We also have to look into that. But if it's just a polynomial, we just, set to 0. So let's take note of that. So we just have to kind of set this to 0 so that we know the point of inflection. So we'll say that set g prime of that to 0. So on that note, so this implies they're going to have 60x minus 120x to the power 3 being set to 0. Okay, so we can, at this point, we can, factor out 60x, and that should give us what? 1 minus 2x to the power of 2, equal to 0. Now we're going to have x equal to 0 as 1. And then remember that we have 1 minus 2x squared equal to 0, right? So in that case, our x should be equal to what? Our x squared should be what? Half, right? Our x squared should be half. But then when you kind of take the square root on both sides, you're going to have plus or minus what? Root of 2 on 2. Very good. So let's take note of that. All right. So we're going to have these values of that. Now, what we are going to do is that for each point of inflection, or for each value that we just got, x values, we're going to plug it back into the main function or the main problem. Is that okay? So we are going to do that. Now we plug. So the first thing to do is that we have f of x. We plug x value into that, and that should give us what? Remember, our x was, this is our x, oh, sorry, our main function that we're given, which is 10x. So we are given, let me use a different pencil here so we're given g of x equal to 10x to the power 3 minus 6x to the power 5. Is that okay? Good. So now what we're going to do, we're going to evaluate such function at each x value, okay? So by doing so, we're going to have, when you plug in that, you're going to have the first value going to 0, and then the second one, so we evaluate it at root of 2 on 2, and that should give us what? That should be 2.47. So let me take my time to do it. So we have So we have 10 of root of 2 on 2 to the power 3 minus root of 2 on 2 to the power 5. And that should give us 2.475. Okay. And then the last one, so why don't I say plus or minus here so that I save myself? I mean, I save the time in doing that. So over here, I can just conclude that 0, 0, and then plus or minus root of 2 on 2, and that of plus or minus 2.475 as the point of inflection, okay, on the graph. So let's take note of that. I think most of you would like this because this is straightforward. Okay, so the first thing to do is to find the second derivative. Then you go further to find second derivative. To first thing to do is to find the first derivative. Then you go further to find the second derivative. Then you set the second derivative to 0. Then you get x values. Then what happens is that we have to evaluate the main function or the main given problem at the x values that you just got. Okay. Then what you do is afterward you kind of put them together as coordinate. Then those points becomes your points of inflection. Okay. I think this is very interesting. I think everybody would like this for some test. All right. So what about, let me say, okay, let's get the next problem of the day, of the night, and would maybe would pause here. Then in the subsequent episode, I would look at other interesting stuff that I think would also be something that I think would make you love math the more. All right. So we are given this particular problem to solve. We want to determine the point of inflection for the function given by k of x equal to e to the power x minus e to the power x. Okay. Already we are very much familiar with this particular function. So what we need to do is to just go straight to the point because we solved it before. So the first thing to do is to kind of, find the first thing to do is to find the first derivative, and that should give us what? 2 multiplying e to the power 2x minus e to the power x. Then we find its second derivative, and that should give us what? 4 multiplying 2x minus this. Then what do we need? The next thing to do is to kind of set this to 0, right? So let's try to, so we say that the point of inflection, the point of over here, I would say that the point of inflection, okay, occurs, the point of inflection occurs when k prime prime of x is equal to what? 0. So this implies that we're going to have, so from this, we can pull out the e. So by pulling out the e, we're going to have something like that we set to 0. Then remember that we said that e to the power x can never be 0 for all x, or for all values of x, okay? So we said that this can never be 0. So the only instance that we can have, the only thing that we can rely on is the other thing, which is 4 multiplying e to the power x minus 1. Is that okay? So with this, we're going to have e to the power x equal to 1/4. And with that, we're going to have, by applying the natural log on both sides, we're going to have something as this. Okay, so we're going to have x equal to the natural log on point, that should be 0.25, okay? Now, what we are going to do is that we are going to plug this, that's what we said. So we need the y coordinate of this potential inflection point. So we need the y coordinate of this potential inflection point. So what we do is that we go to the main function, then we evaluate it at where x equal to the natural log of 0.25. Remember that our k of x, which was the function that we're given, was e to the power 2x minus 2x, right? Minus e to the power x, right? So we're going to evaluate that at natural log of 0.25, okay? So you're going to have e to the power 2 multiplying or minus e to the power natural log of 0.25. On that note, you're going to have 0.25 to the power 2 minus what? 0.25. And that should give us what? Minus 3 on the 16. Do we see that? All right, so at this point, I want us to be more inquisitive. All right, so now let's determine if there's a change in the sign of the second derivative on either side of this potential inflection point. And over here, I want to kind of point out that this is equivalent to negative 1.386. If you use a calculator, you should get something like this. So let's try and find out if there's a sign on either side of this potential inflection point. Okay. So please let's kind of take note. This should be a inflection point here. So let's take note of that. Just going to be more inquisitive. That's one thing about mathematics. Sometimes you have to be very inquisitive just to see if everything is okay. Being inquisitive in mathematics is very key. It's very important. Once you are like that, you will always be on top of the game. All right, so let's try and find out. Suppose that we are on a number line as this, and we have, remember this is your x line, and then we are at negative 3.386. So we can pick some values here. Let's pick probably 0 here, and then let's pick 2 on the right side. Okay, then we plug that into the second derivative and see what will happen. So let's test. So for the text, so we pick 0, then we plug it into the second derivative. Remember the second derivative we had what? With the second derivative, let me write it here. The second derivative we had 4 multiplying 2x to the power that, right? So we evaluate this at 0. What do we get? So we are going to have what? 3, right? And then we kind of also test for the other side, which is 2. And when we plug it into the f prime prime, and that should give us what? Okay, I think that let me rather pick, no, we cannot pick. So let me rather pick, switch the positions here, sorry. So let's rather pick negative 2 here. I rather made a mistake by putting them on the other, on the wrong side. So let's take note of that. So at negative 2, yeah, it's negative, sorry. So at negative, we should have what? At negative, we should have negative 0.06. Okay. Now over here we see that there's a change in sign. Okay. If the sign were the same, would have said that there's no point of inflection. Suppose we had positive values, that would say that there's no point of inflection, or if there were also negative values, okay, we'll say there's no inflection. But since there's a change in the values or in the sign, we claim that there's a point of inflection. Okay, so the coordinate. So we claim that lane of 0.25 and negative 3 on 16 is a point of inflection. So let's take note. At this point, if you have not subscribed, please do so. Like, comment, and turn on the notification button so that anytime I release new content, you'll be the first to have them. And also try your best possible to post these videos, share it with your loved ones, your colleagues, and let's help to demystify the myth around mathematics. Stay blessed and continue to enjoy my content.